Hi everyone. Today we'll be going over ObserVIEW 2023.1. This is a very big release for us. This has the largest amount of features in it of any release we've done yet. And the way I'm going to present the feature changes today is a quick demo walkthrough of how I use each feature analyzing data myself. The large headline changes in this version are going to be the graph pages or the dockable tabs for graphs where you can put them on multiple monitors or arrange them on top of each other. There's a text import tool that's very robust, lets you open up data from other data acquisition systems. And there's now very refined and capable time math channels and math traces that give us a very big boost in capability. There's not a day that I analyze data with ObserVIEW and I don't use time math traces or math channels. So that'll be really fun to show off. And then the last thing I want to show is this new feature we have for aligning and overlaying data files based on the atomic time from GPS data. So because GPS works on the concept of atomic time, we can use that to realign files that are collected from multiple data acquisition systems so that they're perfectly aligned with one another. Beyond those headline features, we also have things like improved Modal custom project setup, the ability to define user-defined units, adding annotations to graphs, just arbitrary annotations. So you could say like this point is out of tolerance, for instance. Cursors on spectrograms, RMS cursor on pasted traces, some basic time history math statistics functions like looking at the mean, kurtosis, and RMS over time. We can also analyze tachometer channels with Live Analyzer. And there's also an output function generator on the observer where you can generate things like sine tones, sine sweeps, and random data. Okay, so this is ObserVIEW 2023, and I'll give you a quick tour of how the tab system works. It's going to be just like you would expect tabs to work in other programs that have tabs, like Vibration View. We can just drag a tab to reorder. We can drag a tab out, and now it's on its own window, where I could then put this onto another monitor if I wanted to. And drop that back in here. One unique feature of how we've done tabs is if you double click on a tab, it will maximize that tab for the current window. That can be helpful so that you can have multiple tabs defined side by side, and you want to temporarily look at something in full screen. Another unique feature of the way we've done tabs is I can take a single graph and I can maximize it, and that will fill the entire application window, and then I can restore it back down. So these have been really useful for us, especially as we add more and more analysis capabilities to the software. Another change from previous versions is the legend is now a bit different. To modify the legend for each graph, you must click this pencil icon, and then you'll see a list of all traces. If the trace that you're looking for is not here, you can click on Add, and then that'll give you a list of additional traces that we could add, and then that will add the new trace right here. So I'll just delete that off there because I didn't want it on there to begin with. So that is the tabs, the pages, and so on. Some other cool things you can do. Let me open up like a simpler file, like this one here. What I'll do is I'll customize my graph layout. Let's say we'll add a SRS graph and perhaps a PSD. And I'm also going to add another page to the side here, tab to the side, and we'll look at transfer function and coherence. This is also new here, this little plus button. I can do a quick add of a graph. So that would be cross-spectral density. Another new change is I actually didn't want cross-spectral density. I wanted coherence. So I can go down to switch graph type right here. And then I can quickly switch this to a coherence graph. So pretty cool. I can see right now too that I don't have enough lines on this PSD. So I'm going to change it here. Looks like I'll need about 65,000 lines. And now that looks better. Another thing here is my SRS doesn't have enough lines. So I'm going to change the upper limit on this. Pro tip, you want to get to the SRS about to the point where you see it plateauing, like it is here. If you're not getting it up to that point, then you might not be capturing the full bandwidth needed for that SRS. So now I've gotten this all laid out. Actually, I think I need this to be a little smaller, and that's because this is a very short waveform. But anyway, now I have this all laid out. I can save this as a graph layout. So there's a few ways to do that. I can go to the graph tab, and then I can say save all graph tabs, or I can save just a selected tab, or I can save the selected graph. But I'm going to do all graph tabs and name this my SRS analysis layout. So now if I have another file like this and I want to analyze it in the same way, I'll just reopen this as a raw file again. All I have to do is click on Add Graph, replace the current graphs, and I'll scroll down and I have my SRS analysis user template here. Add that in, and now I've applied the same graph layout that I had in my previous analysis to, let's say, another file. So, pretty good time saver there, very useful, and we use it all the time. So that's that. I'm going to go back over to looking at our bike analysis here. Let me give you a little background on how this bike analysis works. The premise here was to take a look at field data on 3 different bicycles and see if we could come up with some kind of a standard test regimen for electric bike batteries. Because everybody's kind of worried about, are these batteries going to catch on fire while they're being charged? And because that is unfortunately a common occurrence with these. So on the left here, we have a Venton e-bike. It's got the largest battery of all of these bikes. In the middle here is a Trek Dual Sport Plus that has a much smaller battery, but it's still an e-bike. And on the right, we have just a conventional Trek FX2 bike. All great bikes, but the thought was, well, maybe the heavier battery or the heavier bike is going to have more vibration, and we should be testing that bike appropriately. What I found when we did analysis on this was something a little counterintuitive, and we'll get into it as we look at the data. But if we look close here, I've got the sensor mounted on the what's called the down tube, or the angled section of the bike. It's a triaxial sensor, and I have it mounted in the same spot, kind of by the water bottle cage on each bike. And the idea we have here is we can mount the accelerometer on an angle, about 60 degrees in each of these bikes' cases, and we can use a math trace or a math channel to correct and reorient the sensor to vertical. This is done in the time domain and creates like a completely new math channel or waveform channel. From that, then we can do all of the normal analyses like PSDs, FDS, and so on the new math channel that gets created. So I want to take, again, this triaxial sensor that's mounted on this down tube at an angle, and I want to create a virtual sensor that's pointing straight vertical and straight fore aft. The equation to do that is just some trigonometry. We include this equation in the help file as an example so that you can also do this yourself. And this is the equation here. It'd be x prime, let's say the new fore aft, is going to be the z on the sensor right here times the sine of this angle plus x on the sensor, which is pointing down in this case, times the cosine of the angle. And then the z, the new z prime, is going to be the z-axis times cosine theta minus x-axis recorded times sine theta. And this is what that looks like in ObserVIEW when we add a math channel. So we'll take, channel 10, that's what V10 is shorthand for. Channel 10 times cosine of degrees to radians, because the cosine function takes radians, minus channel 8 times sine degrees to radians, 50 degrees. So that would be how we do it on the Trek FX2. Now I'll pop over to ObserVIEW and show you how we do that in the software. So I've got this down tube time history, and let me modify it a little bit so we're just looking at the raw data right there. So down tube vertical, down tube fore aft, down tube lateral. Add a math channel, which brings up our math dialog. And just in the interest of time, rather than recreating the math channel, I'm just going to look at the one that's already created. So I've got this V3 times cosine of 60. This is actually going to need to be deg 2 rad 60, because these trig functions take radians. And this is like a pretty similar concept to doing trig in Microsoft Excel. It's also going to take in radians, and it has a similar set of functions to what I'm showing you here. So now we got G in, G out, and that creates a new virtual math channel, vertical right there. Here's our down tube fore aft. We're going to need a deg 2 rad here. Just typing that out. There we go. And then we have lateral. The nice thing about lateral is it's just literally channel 2. I did this as a quick way to do basically a channel rename. Rather than renaming the channel, which I can do a different way, I just created another math channel, and then I renamed it. So Nothing to worry about there. While we're in here looking at the math options, here are all the functions that we have available for the time or the math channels. Huge selection of things like absolute value, ceiling, floor, trigonometry functions, power, exp, log. You can do statistics. Getting down into there, you can do high pass filter, low pass filter, integration, differentiation, see, standard deviation, RMS, variance, kurtosis. So a very wide range of functions that all have their own purpose, and I'll get into a couple more of them as we go here. So anyway, here's our nice down to vertical. Let's apply that function. And this is the corrected triax data where it was mounted on the angle, and then we corrected for that angle. And now we're looking at what the vertical is after correction. We can now also create a PSD from this. So I'll just do PSD. And here is our PSD off of the math channels. So really cool. When you create a math channel, we're actually adding that as additional channels that can be computed with things like a power spectral density or a FDS. So there we are. That's our PSD. So next up, let's take a look at adding in some math trace functions. So we were just looking at math channel functions that are adding additional math channels or different additional channels. Let's say I want to get an average of these three PSDs. To do that, I'll just do add math trace on PSD, and then I'll do max of, and then I can search here down to, and I can just add these three in like this. Now we have an additional math trace that is basically the envelope of all of the traces that you have on this graph. That's pretty useful. Let's say instead of the max, I want the average, so I could do mean. And now we're looking at the mean instead. So let me change this to a nice vibrant color, make it thick. And now you have a live updating mean PSD, like that. Now, this exact example that I did, you don't want to do. I just got the average PSD of three axes. A more practical thing to do would be to get the average PSD of, let's say, 2 or 3 vertical accelerometer channels. Some statistics things that we can do are right here. So I've got a few of them defined. Here I'm looking at the RMS versus time, the kurtosis versus time. And those are pretty useful. Let's take a look at adding one of those in from scratch, just so you can see how to do it. So what I'm going to do is I'm going to copy this function here, and I'm going to do RMS of this, and then the output of that is going to be the vertical RMS. So that's added our new RMS trace. Unfortunately, that adds it on top of the data up here. It's a little bit small. And because it's basically a different unit, I'm going to change the output unit to something called GRMS, which is something I can just create and just give it a new unit in here. Let's get rid of these other ones quick. So here's our vertical RMS over time. So another thing that I can do with this is I can change the time constant on the RMS calculation. So right now it's defaulting to a 10-second rolling average. I could make that a slower average by saying I want a 60-second rolling average. So I'll do that quite often. Just makes it more tame to look at. Another statistic that I like to add is the kurtosis over time. So I'll duplicate this RMS one here, and I'm going to switch this from RMS to kurtosis. Switch that to kurtosis, and I'll switch the unit right there. So here we are looking at the kurtosis of this data over time. This kurtosis is relatively high. Random data is going to have a kurtosis around 3. And this data is moving between 10 and 30 kurtosis, which is telling me that it's not very random data. There's a lot of spikiness, let's call it, in the data from hitting potholes and so on. And when I would go to create a test for this, I'd strongly recommend to use the kurtosis control feature of VibrationView. And I used this kurtosis trace as an indicator of what kurtosis I should use when creating a PSD with FDS. So just to give a demonstration of that, let's add in a FDS. Okay. And we want to do just this rear vertical. And it's set to a kurtosis of 40 right now. And let's take a look at the kurtosis on here. So I've got a kurtosis in this section of 26 to about 10, and I can kind of look over the trend of this. And I'm going to pick about a kurtosis of 25. Looks pretty consistent there. So we'll click on the FDS, set the kurtosis to 25, and that is it. Then I could take this FDS test spectrum, which is a PSD, and I could run a vibration test off of that using a kurtosis control of 25 kurtosis. So as you can see, there's quite a few math operations that we can do. And some additional math operations can be found in the help file. So if I open up the help dialog, go here, and this gives us an overview of what the math channels and math traces are and some examples. And I think these examples are just really helpful. So here's how you do an envelope of multiple PSD traces, create an average PSD trace. We just showed those two examples already. You can scale a value by just multiplying it by a number. You can divide and get a ratio. If you want to find the absolute acceleration or total power of a triaxial sensor, that's going to vary based on the unit. So an FFT or an octave is going to be square root of the sum of the squares. And then for a PSD, it'll be just a sum. Another example, if you're looking at controller data recorded into a VFW file, maybe you want to get the transmissibility of an average control channel. So the control channel in this case would be 4 channels. It's going to be channel 1, 2, 3, and 4. And you want to know channel 5 over the average control channel. So the equation for that is going to be square root of channel 5 over the mean of channels 1 through 4. And yeah, we won't go through all these. I do find this one quite helpful. This is adding something called a coherence mask to a transfer function. What this is doing is you can do a transfer function. It will give you results. And what we tell people is you should only trust these transfer function results if the coherence is, let's say, above 0.8. There's a few ways that would be nice to kind of visualize that. You could put the coherence trace, for instance, just on top of the transfer function and then kind of compare things that way. Another way to do it is we could combine the coherence and the transfer function together like this. So if I take the transfer function times the coherence, where coherence is greater than 0.8, that will kind of do a piecewise breakup of the transfer function and only show you transfer function data where the coherence is above 0.8. So that's what this green line you see here is. Another way to do this is to add a coherence trace to a transfer function graph and hide it, but then set that coherence trace as a tolerance. And so that's what is being shown here, where it's going both red and green depending on if it's in coherence or not. You can also add tolerance lines centered around a pasted demand trace. So if I paste in a demand trace, this middle line here in red, I could paste it from Excel or wherever. I can also then create the tolerance lines automatically based off of that pasted demand trace. And the way to do that is to multiply the pasted trace, call it demand, times 10 to the 3 over 10. That's going to be a 3 dB tolerance. And then if you want the negative 3 dB tolerance, it'll be 10 to the negative 3 over 10. A little interesting here too, you can also convert an octave filtered trace into a PSD trace. We have had customers ask how to do this in the past, and this is the equation to do that. So just a lot of stuff that's possible. And then you get into the math channels, and math channels are a whole nother thing. A lot of the same types of functions that you have in the frequency domain, and some that are unique to math channels. So one of those that is unique is applying low pass and high pass filters to individual traces. So that can be helpful if you want to apply a high pass filter or a low pass filter specifically to certain channels, but not all channels. We make it really easy in the software to apply these filters to all channels, and this will give you a way to do it just to some channels. The syntax for adding like a low pass filter is going to be LPF, the channel, and then the corner frequency. So this would be a 2000 hertz low pass filter. High pass filter is simple. That's just going to be HPF, same idea. If you want to do a band pass, you can do a low pass filter of a high pass filter. So this would be a bandpass from 10 to 2000 hertz. Finding the absolute acceleration of a triax. This is the equation, square root of v1 squared, v2 squared, v3 squared. Pretty useful. And I'll just kind of go down here. We also can do integration and differentiation. So you could convert acceleration data to velocity or displacement. Just a matter of doing the right order of integration and then specifying the correct units. And all of the examples for that are in here. Decibel conversions. And then this one's, kind of cool. We can generate just arbitrary waveforms. So if you do rand_n, that will do a random number sequence. And if you do a PSD of that random number sequence, it'll be a nice flat line in the PSD. We can also do sine tones. So here's an example of doing sine just with pure math. So sine of time times 30 times 2 times pi is going to be a 30 hertz sine tone. You multiply by 5 on the outside, and that's going to be your scalar to go from 1G to 5Gs. Here's a square wave example, sawtooth, triangle, sine suite, and so on. So really cool stuff. There's a lot you can do with math channels and math traces, and I think you'll get a lot of use out of them. So getting back to the discovery that I found when looking at this data with the bike. Let's open up the data and do an overlay of multiple bikes. And I did get a touch ahead of myself. The way that we constructed this data file is kind of unique. It's actually a recording from 3 observers that were done at the same time and 3 different bikes at the same time. And that's kind of apparent if we take a look at the video. So I'll just make sure that's muted here and go backwards. So you can see we're all kind of riding bikes together. We have the video synchronized, so you can see everything all together. And we've got the map view here, so you can see we're going through this cul-de-sac. I could click play here and you can see where the data is. So this is how we made sure that we were all going the exact same speed between all these bikes. We literally just went at the same time. And then the data is also going to be very, very aligned doing this in time. The way that we brought all the data together is a new feature in the batch file processor. I can open up here. It's called overlay and align files using GPS. What I did is I added the 3 files here, and I said align these using GPS timestamps, and it took the 3 files and put them into one and resampled and aligned everything perfectly. So that is the file that we're looking at here. And when you do that, you just kind of rearrange some things here for make it easier for me. When you do that, we get all of these additional traces. I'm just going to turn off the math ones here. And here is that data set of the 3 bikes put all together. So I've got the event in here on the top, and then the track dual sport, and then the track FX2. All right. Now let's take a look at the PSDs in the vertical direction. So we have the heavy bike, the Aventon, the medium weight bike right here in blue, the lightweight conventional Trek FX2 bike at the top here. Now, what is interesting about this? Well, I thought intuitively that a bike that has a heavier battery is going to experience more vibration, and that is not the case. What has happened is the heaviest bike, the heaviest down tube, because it has a large heavy battery in it, actually has the least amount of vibration. So this is the PSD. I can expand it out a little bit further so we get a little more averaging, but it's very consistent. The PSD is just lower on the heaviest bike, the heaviest battery. And I've got a RMS of 0.21 on the GRMS on the heavy bike. The next bike is another electric bike, but with a much smaller battery. It's half the size. And this bike has a very similar PSD profile to it. You know, you got this hump here down around 27 hertz. And then it kind of drops off after that. But overall, it is higher. And if I look at the GRMS, it's 0.31 versus 0.21 GRMS. Okay, so interesting trend. Let's see if it continues. Now the lightest weight bike, there's just the normal bike without a battery in it, has much higher acceleration. The RMS of this PSD is 0.58 GRMS versus 0.21 on the heavier bike. So what's going on here? What is happening is at the spot that this sensor is mounted is right by the battery. So it's going to be impacted by the battery's inertia quite a bit. And if we look at F equals MA and we keep F force pretty consistent between these three bikes, which we did, and then we vary the mass, so we increase the mass, well, the acceleration has to compensate for that. So if we increase mass, we need to decrease acceleration in order to maintain the same force. And that's what's happening here. Basically the higher inertia of the heavier battery is lowering the acceleration. And I did confirm this in another way. I took the battery I just removed the battery out of the heavy bike and reran the test and overlaid it, and the e-bike with the battery removed had higher acceleration at that point. It's a pretty interesting result. What I would still recommend I do out of all of this is I'm going to take this data and I'm going to add a math trace. And I think what I'm going to do is I'm going to do the mean, and I'm also going to take the envelope of this, and I'm going to determine if I want to test to the worst case, which is going to be the standard bike, or to the average of this to make as my test profile. So just very simply, we'll do a mean, and let's do down here, vertical. And now we have our new candidate test profile. It's going to be the average PSD of our three test bikes taken on the same course. So pretty cool. Learned something doing that analysis, and it would be an interesting recommendation going forward. The recommendation being that heavier bikes might require less vibration, just based on the fact that they're seeing less vibration in the field. So let's see if I've covered most of the things here. We've got the ability to plot the GPS data as a graph. So if you click this button here on the GPS, it will switch over to showing you the GPS data plotted on a 2D graph. So I can track velocity over time and latitude and longitude over time. This right here is actually the altitude above sea level over time. It's a little bit of a discrepancy there, but yeah, interesting. Let's switch that back. We can add annotations to graphs. It's kind of like adding a cursor, but just putting in a note. So if I look here, this is an annotation, and you can just make a note on the graph, and that is nice to put into a report afterwards. You can add cursors to spectrograms, RMS unpasted, just a lot of things. Very big release. We're pretty proud of it. Adds a lot of capability to ObserVIEW. It's going to help us make really good engineering judgments on the data that we have going forward, and lead to making really great tests off of the vibration data that's collected. Now that I think about it, I have missed one big thing, and that is the file import dialog. So let's end it on that. I'll create a new ObserVIEW here. And what's so cool about the enhanced file import dialog is now we can open up some CSV files and text files from other data systems, data collection systems that didn't open up as cleanly before. So here I'm opening up a file, and it's struggling a little bit to open. It didn't fully handle everything quite right. So I can click on text import settings, and I can look at this raw data, and I can inspect things, and I could correct the sampling rate, for instance. I could correct the units that it's using, and so on. So that date column is bad. I could specify a different unit than the one it detects and reopen it. So that's one file. Let's try another one. So let's say you get a data file like this, and it's just 3 channels of data with no sampling rate defined. Let's see. Yeah, no sampling rate defined. So let's go and fix that up. So I know the customer told me it's 2000 hertz. The data is going to start at that row. It doesn't have a unit row. The customer told me it's meters per second squared. There you go. So now I've got the data coming in as I need it. It looks like this middle column is just 23 the whole way down. Interesting. And that'll open up. And there's our data. This one's kind of big. So this one is from a flight controller on a drone, actually. That's got a sampling rate of 2000 hertz. Data starts at row 2. And that'll kind of fix things up a bit. The names are coming from row 1. Let's say the units are not quite right, so I'll just nix that. And then I know my default unit should be meters per second squared on this file, so I can change that. And then we can turn off a few of the channels that don't make sense. So I'll turn these ones off here and click OK. And now we have our data. Pretty cool. And I could do a PSD of that. And so now I'm looking at analyzing flight controller data from a drone, just to give you an example. So pretty robust file import, pretty proud of that. And should let you bring in data from things, combine it, and make really good engineering analysis and test definitions. So that's all I have to cover on ObserVIEW 23 today. Huge release. We're really proud of it. Lots of things that you can do now that you couldn't before. Many of the things I did show, just FYI, are in the advanced module. So the math functions are all going to require advanced. And you can use the trial license that I provided in the chat at the start of this recording. I'll also send that out to you later on. So if you have any questions, let me know. I'll stick around for just a little bit longer and I can answer those questions. Thanks.